This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Right, I think we should make a start. Alright, so we are in lecture 13 now. So this is the second last week of potential flow. Right, how many of you have not found a partner for your assignment? Is there anyone still who has not? Alright, if you have not found a partner yet and you are finding a partner, send me an email, alright, and I'll just link you guys together, alright. I thought that most of you would have actually started the assignment and would have found partners, but anyway, alright, I hope that at least most of you have done question 1 and 2 and hopefully 3 of the assignment, right? Should be fairly quite straightforward, but I'll talk more about the assignment later this week on Thursday, right, and show you some tricks on what you should have in your assignment, especially when drawing the streamlines. Okay, right, so just a quick recap on what we did last week on Thursday. So I've introduced the potential vortex to you guys, right, which is also known as a point vortex. I introduced this term called circulation, and we also then derived the stream function, potential function, and the complex potential for a potential vortex or point vortex. Right, so we have defined our potential vortex or point vortex so that it has an only azimuthal velocity, right, which is equals to c divided by r, and has no radial velocity. Okay, and that gives you circular streamlines. Okay, so if you consider an element on a streamline and we calculate its vorticity, we found that it has 0 vorticity, right? So a vortex defined as such is irrotational-ish, right? Except at the center where it's rotational, right? Where r equals to 0. So at the singularity, it's rotational-ish, right? But everywhere else, it's irrotational. Right, and circulation gamma, we've defined it as the line integral of velocity around a closed loop. Okay, and for our potential vortex, it's a bit easier, all right, because our velocity u theta is always perpendicular to the streamlines. Sorry, it's always parallel to the streamlines. So when we calculate the circulation for our potential vortex, it's just u theta 2 pi r. Okay. Right, and if we rearrange this to obtain an expression for u theta, we can then compare it with our definition of a point vortex, which is equals to c divided by r, and we get that our constant c is just gamma divided by 2 pi. Okay, and we also found that circulation is also equal to the area integral of vorticity, right? So if you have a circular surface as such, you know that the circulation for that surface is 2 pi c. Okay, even for this surface, the circulation is 2 pi c because it wraps around the point vortex. Okay, but everywhere else, your circulation is going to be 0, right? It's irrotational. All right, and then we derived psi. So using our definition of a stream function in cylindrical polar coordinates, okay, we get psi equals to negative gamma divided by 2 pi log R. Okay, and that's your stream function for a potential vortex. And gamma, which is our circulation, right, is basically, I guess, a measure of how strong your potential vortex is, right? Similar to a source or a sink, where Q, your flow rate, defines how strong your source and sink is. Here, circulation gamma tells you how strong your potential vortex is. Okay? And using the relationship between phi and psi, we can then derive our potential function for a potential vortex, right? And the complex potential is just equals to phi plus I psi, right? Which gives you W equals to negative I gamma over 2 pi log Z. Okay, everyone's clear so far? Yep, just a quick refresher. Right, and to obtain the velocity for a potential vortex, all you have to do is just differentiate W with respect to Z. Okay, and the real part gives you U, your velocity U, and the negative imaginary part gives you V. Right, and in MATLAB it's really easy to draw the velocity vectors. Okay. Right, so this is your potential vortex, a single potential vortex. But if you have two potential vortex, it can induce motion, right? So the potential vortex on the left is rotating clockwise, right? And the one on the right is rotating anti-clockwise. And as we have shown previously, both of them would move, push each other downwards. Okay. And we have another case where both of these potential vortex are rotating clockwise, and they mutually induce each other, and they rotate. They cause each other to rotate, right? And when you have 3 or more potential vortex, predicting, I guess, its trajectory is a bit hard by pen and paper, but very easily done in MATLAB, right? All right, so far we have learned 4 basic building block flows, right? So we have on the top left our uniform flow, on the right our potential vortex, and at the bottom we have our source and sink. Okay, and it's expected that you know how to derive the potential function, the stream function, and the complex potential for all these basic flows. Okay, and when we have a source superimposed on top of a sink, what do we get? A source plus a sink. A doublet, right? Okay, so you should also know the potential function, the stream function, and the complex potential for a doublet as well. Right, and please be careful with the signs. Make sure that you know that if it's negative, you know that the streamlines are rotating in the anti-clockwise direction. Okay, just be careful with that. All right, today we're going to look at the flow of a cylinder plus a point vortex. Okay, right, so we know that this term here is for the flow of a cylinder, right? And now we're just adding a second term for the potential vortex, which is located right at the center of the cylinder. Okay, and the flow is flowing from right to left. Okay, and the potential vortex is rotating anti-clockwise, right? Because there's a negative here. Okay. Now, this is a past exam question, right? So, in this question here, you have given phi and psi for this flow of a cylinder with a potential vortex. Okay, and the first part is you're asked to derive the complex potential function, all right, W for this flow. Okay, and it's worth 3 marks, right? Quite a bit. Okay, and next we are then asked to demonstrate that the existence of the stagnation points on the cylinder surface will depend on the parameter gamma divided by 4 pi u infinity a. Okay, so let's try and do this question together. Let's do part B first. Let's find our complex potential and find our velocities UR and U theta. Can you all hear me? I was getting a bit of feedback, but I think maybe this is better. Right, so the first step in this question is to find the complex potential. Right, so W just equals to phi plus I psi. Okay, and I'm just going to substitute what phi and psi are given in the exam questions, which is just U infinity cos theta A squared over R, sorry, minus A squared over R minus R plus gamma theta over 2 pi. Plus I U infinity sine theta A squared over R minus gamma over 2 pi ln R over A. Okay, so we want to express all of this here in terms of z, right, our complex number. So we have to do a bit of factorizing. Okay, so I want to get this cos and sine terms to be grouped together. Okay, and this term to be grouped together as well. Right, so I'm going to get negative U infinity cos theta minus I sine theta A squared over R plus cos theta plus I sine theta R. Okay, and it's going to be minus gamma I over 2 pi I theta plus ln R over A. Yep, so this term, well, this term here, basically I've just equated to be negative I squared, right? So this becomes negative, I add a negative I squared here, so that I can factorize it as such. Right? Okay. Now, right, so I want to put it in terms of cosine plus I sine, because I know, well, hopefully you all remember that, what's that equal to? Cosine theta plus I sine theta, what's that? Right, good. So cosine theta plus I sine theta is just equals to R, sorry, there's no R, it's just E I theta, right? Okay, and hopefully that you know if it's minus, it's just negative I theta. Okay, well, this is just a side note. I hope you guys know that. Okay, but substituting that, I'm going to get negative u infinity e negative I theta a squared over r plus r e I theta minus I gamma over 2 pi ln e I theta plus ln r over a. Okay, everyone following so far? Yep. So I know that this term here is going to be 1 over z, right? Okay, so I can just write negative u infinity a squared over z plus this term here, which we know is also z, minus I gamma over 2 pi. Right, and this term here, I'm using the same trick which we did in the last lecture, right? So I theta, I'm just going to put it as an ln exponent I theta. Okay, because I can then combine this term with this term here, which would give me z over a, right? So it's just going to be ln z over a. Right? So if you do not know this trick here, if you do not know how to get from here to here, it will be very difficult for you to get to simplify this term here into z over a. Right? So please remember this trick. Right? Okay, and just for a side note, I'm just going to put z equals to r e I theta. Well, I'm sure most of you know that. Okay? Everyone's following so far? Yep. So this is your flow over cylinder. Okay, and this is for your potential vortex. Right? And maybe I should also put some note. So where's my uniform flowing for this for this flow over cylinder? Left to right or right to left? Right to left, okay? So it's right to left. Okay, and for this potential vortex, is it rotating clockwise or anti-clockwise? Anti-clockwise, okay? So it's very important to know your flow direction. Okay, if you do not know that, then it's going to be really hard for you to sketch the flow later on. Okay, so first step done, we found the complex potential. The next step is to find our velocities. Okay, so finding our velocities from our complex potential is quite easy. It's just going to be dw dz. Right, let's just differentiate dw dz first. So we're going to get negative u infinity 1 minus a squared over z squared minus I gamma over 2 pi z. Okay, and in this case, working in cylindrical coordinates is a bit easier. Okay, and we know that exponent I theta dw dz gives you gives you ur minus I u theta. Okay, so we know what dw dz is. That's just this term here. So we want to multiply this whole right hand side here with exponent I theta. Okay. Oops. dw dz. Okay, and I want to substitute z equals to r e I theta. Okay, so therefore I'm going to get negative u infinity exponent I theta 1 minus a squared over r squared e I 2 theta minus I gamma over 2 pi r e I theta. And I'm missing another term at the end here, which is exponent I theta. Right, everyone agree? Yep, so can cancel these two terms off. I can cancel one of the theta here as well. Okay? So I end up with negative u infinity exponent I theta minus a squared exponent negative I theta over r minus I gamma over 2 pi r. Okay, and I'm going to substitute exponent I theta equals to cos theta plus I sine theta. Sorry, did I make a mistake? Here? Yeah. Yeah. Sorry about that. Yep. Let me just check. Yep. Okay, so I'm going to substitute exponent I theta with cosine theta plus I sine theta. That's just Euler's formula. So I'm going to get negative u infinity cosine theta plus I sine theta minus a squared cosine theta minus I sine theta over r squared minus I gamma over 2 pi r. Okay, so what I'm doing here is basically I'm just expanding all the terms again, alright? Okay, I'm substituting Euler's formula. I want to expand the terms because I want to separate between my real and my real and imaginary terms. Okay, so that I can find what UR is and what U theta is. Okay, so factorizing all my real terms, right, I'm going to get negative U infinity cos theta minus A squared over R squared cos theta. Minus I, okay, all my imaginary terms. Oops. U infinity sine theta plus A squared over R squared sine theta plus gamma over 2 pi r. Okay, so these terms are all real, right, which means it's just equals to UR, my radial velocity, okay, and these terms here are all imaginary, okay, which means that negative of the imaginary component is my azimuthal velocity. Okay, is everyone clear? Yep. There was a what? Sorry? Oh, this one. This one? Yep. So when you differentiate it, the A drops out, right? Right? No? So you can expand this term here, right? So I can write it as negative I gamma over 2 pi ln Z minus I gamma over 2 pi ln A, right? And then when I differentiate it, I won't have the A term there anymore. So I just end up with this. It's just this term. Yeah. Oh, sorry, it's so small. but you got what I... Okay, yeah, so you just end up with this term here. Right? Okay, so you have your velocities U and V, UR, U theta. Now you want to find the stagnation point. Okay, and at the stagnation point, your velocities are 0. Okay, very good. So let's consider the real component first, right? Our azimuthal velocity, our radial velocity. Okay, let's consider that case first. That velocity component first. So let's consider real component. Okay, our radial velocity. All right, so we have negative U infinity cosine theta minus A squared over R squared cosine theta. Okay, and we want our radial velocity to be equal to 0 at our stagnation point. Okay, U infinity is not 0. right? U infinity is not 0, therefore this term here has to be equals to 0. Okay, so cos theta equals to a squared over r squared cos theta. Okay, and there's two solutions to this equation, right? So one possible solution is when r is equals to a. Okay, everyone agree with me? Right? So when r equals to a, then you're going to get cosine theta equals to cosine theta, right? So that's one possible solution. What's the other possible solution? When theta is equals to? Pi over 2. Very good. Okay, so we know that when cosine pi over 2 is just equals to 0, right? So we have two possible solutions. Let's consider when r equals to a first. Okay. Let's consider the case when r equals to a, right? So the radius is on the surface of our cylinder. Okay, so when r equals to a, the imaginary part or u theta okay, so I'll just get u infinity sine theta plus sine theta equals to negative gamma over 2 pi a. Right, so just rearranging it, I'll get sine theta, it's going to be equal to negative gamma divided by 4 u infinity pi a. Therefore, theta is going to be equal to arc sine negative gamma over 4 pi u infinity a. Okay, is everyone following so far? Yep, so I just rearranged this equation here so that I get theta in terms of gamma, u infinity, and a. Alright, so this is the case when your stagnation point is when r equals to a, alright? So your stagnation point is along your cylinder, right? It's on the surface of the cylinder, sorry, right? And hopefully you can see that this solution is only valid. You know that sine theta ranges from -1 to 1, right? Okay, so therefore this term here is only valid from -1 to 1. Okay, so I'm going to put a note here. Actually, I'm going to move this a little bit first. Right, so the solution is only valid for gamma divided by 4 pi u infinity a less than 1, right? So the absolute of, oops. So the absolute of that term has to be less than 1. Okay, because you know that this is bounded from -1 to 1. Right? Therefore, this is bounded from -1 to 1. Okay? So, what happens when this is greater than 1? Okay? What happens when this term is greater than 1? Any guesses? Is your stagnation point still along your surface of your cylinder? No, not anymore, right? So we would then have to consider case when, remember we had theta equals to plus minus pi over 2. Right? Okay, so let's consider this case when theta equals to plus minus pi over 2. So again, I'm going to look at the imaginary part, or u theta, right? Okay, so now I'm going to get u infinity sine theta plus a squared over r squared sine theta plus gamma over 2 pi r equals to 0. Okay, and sine pi over 2 is just equals to 1, right? This is going to be 1 plus a squared over r squared. Did anyone say 0? No, right? Sine pi over 2 is 1. Okay. Plus gamma over 2 pi r equals to 0. Okay, so I want to bring r squared to the top here. So what I'm going to do is I'm going to multiply both sides with r squared and rearrange. Okay. Okay, so I want to have it as a quadratic equation. So I can write r squared plus gamma r over 2 pi u infinity plus a squared equals to 0. Right, so I skipped a few steps, but I basically want to write r as a quadratic equation here, right? R squared. So now I want to solve it for r. Solve the equation for r, sorry. Solve for r. Right, and I hope you all know how to solve a quadratic equation, right? If you don't know, I'll just put a side note again. So r is just going to be equal to negative b plus minus b squared minus 4ac over 2a. Okay, so if you do that, you're going to get r is going to be equal to, gamma over 4 pi u infinity plus minus r oops, plus minus gamma squared over 16 pi squared u infinity squared minus a squared. Right? Everyone agree? Oh, is it minus? Yeah, I guess. Oh, shucks. Yeah. Yeah, I made a mistake. I can't believe it. Okay, well, that's life. Okay. Yeah, there is. I think there is a minus, right? Yes. But why didn't we put a minus there? Oh, right. Okay. Huh. I'm not wrong. Okay, I'm not wrong. So remember, theta can be plus minus pi over 2, right? We are only taking the absolute. So I'm going to erase that back. Right? Negative values of r doesn't make sense, right? We can't have negative values of r, right? Because r is your radius, right? It's a radius, it's a length. You can't have negative length. Okay, that's why we are only taking the absolute of it, and that's why there is no negative term here. Okay? Yes, now I remembered. Right? So we're only taking positive values of r. Okay? You can't get negative r. You can't, Well, negative r basically means that it's at the opposite angle, if it makes sense. Okay? Right. Because r is a length, it has to be always some magnitude. It's always positive. Right? Okay, I'll show you the flow field in a bit, alright, how it looks like. And we only know that for r to be valid, this term here has to be positive, right? It can't be negative. You can't have a negative square root, or else you get an imaginary number. So, therefore, right, gamma over 4 pi u infinity has to be larger than a. Therefore, right, it's only valid for cases when gamma over 4 pi u infinity a is greater than 1. Okay, and we get two roots. Okay, one at r greater than a and r less than a. Okay, so because you have a plus minus here, right, and this is a real number, okay, you're going to get two roots. One of the roots will be away from the surface of the cylinder, okay, and one of the stagnation points will be inside of the cylinder, okay. Okay, so hopefully I showed you that this parameter gamma divided by 4 pi u infinity a, right? This parameter here is an important parameter in determining the location of your stagnation point. Okay, so let's go back to the slides. Right, so the flow is moving from right to left, okay, and when you have zero circulation, right, when you don't have a potential vortex, your stagnation point is just going to be at the front and back of your cylinder, okay? It's just a flow over cylinder basically. Okay, but now as I add circulation, right, as I change this, the strength of this term here, okay, as I change the strength of this term, right, you can see that my stagnation point moves further and further downwards, all right, to theta equals to pi over 2. Okay, right, and okay, hopefully you have seen that the location of a stagnation point does depend on this parameter gamma over 4 pi u infinity over a, u infinity a. Okay, and we have looked at when this parameter is greater than 1 and less than 1. Okay, and when this parameter is equals to 1, we only have one stagnation point. Okay. Okay, so looking at this again, right? So now my circulation is 0. Okay, and for the cases where gamma over 4 pi u infinity a is less than 1, right? You can see that the stagnation point lies along your cylinder, right? But the angle theta increases, right? And when it's exactly equal to 1, when gamma over 4 pi u infinity a is equals to 1, you only have one stagnation point, okay, at theta equals to pi over 2. Okay. Right, and when your parameter is greater than 1, okay, theta is going to be located at pi over 2. Okay, and the location, the radial location of these stagnation points would change. Okay, and your stagnation point will be moving further away from the surface of your cylinder. Okay. Right, and the flow field looks something like this as I increase that parameter to be greater than 1. Right, so you can see that my stagnation point has moved quite a far bit from my cylinder, okay, and you can see that the red lines which I've drawn, which is my separatrix, is looks quite a bit different, okay, compared when the stagnation point lies along the surface of the cylinder. Right, if you consider the far field of the flow, right, hopefully you know that the uniform flow is going to be dominating. Okay, right, so far field uniform flow is going to be dominating, but in the regions near to your doublet and your potential vortex, you're going to get this quite, I guess, interesting streamlines. Okay. Okay, so note throughout this condition, a circular streamline is always preserved. Okay, so let's prove this, right? Or to ask that question, or to phrase the question: does the surface of the cylinder remain circular? Okay, when we change this parameter gamma over 4 pi
u infinity a. Okay, so we have to start back from our stream function. Okay, and we want to check if the streamlines, if the surface of the cylinder is a streamline. Okay, so basically when r equals to a, we want to see whether the surface of the cylinder is streamlined. So if I substitute r equals to a, I'm going to get u infinity sine a minus gamma over 2 pi ln 1. Okay, and you know that ln 1 is just equals to 0, so psi is equals to 0. Alright, so psi is a streamline, it's a constant. Oops. Oh. Oops. Okay, so psi is a constant, therefore the surface of the cylinder is a circular streamline. Right? So hopefully you can see that the surface of the cylinder is still a circular streamline, even though we have varied gamma of the parameter gamma over 4 pi u infinity a. Okay? Okay? So if I show back this slide here, right? So even though I'm changing this parameter here, okay, take note that my cylinder is always a circular streamline, right? Which means that the shape of my cylinder does not change. It's unaffected when I change this parameter, okay? Right? See that my cylinder is still the same. Okay, it has a radius of a. Okay, it's unaffected by this parameter here. Okay, and it's because we have shown that psi is a constant on the surface of the cylinder, and it's a circular streamline. All right, so on Wednesday, all right, we would want to then find out the pressure distribution for this flow over a rotating cylinder. Okay, and you can see that there is some asymmetry now in your pressure distribution, okay, which will give you lift. Right, and I'll show you some interesting videos as well on Wednesday. Okay, thank you.